Hello everyone, I'm Colin Kurz, and this is my report for Lab 4, Oscillations. The purpose of this lab was to analyze the motion and energy of a mass swinging on a spring. To accomplish this, a computational prediction of the motion of the mass was created and compared to the actual motion of the mass. The results of the lab show that there are factors in the real motion of the mass that were not able to be accounted for in the model, resulting in some inaccuracy in the model. This lab had two fundamental physics principles: Newton's second law of motion and the energy principle. Newton's second law of motion states that the net force acting on a moving object is the product of the object's mass and acceleration. Derived from this law are the velocity update and position update equations, which were used in this lab. Also important is the concept that net force is equal to all the forces acting on a system added up, which matters because this lab involves the use of two forces: gravitational force and spring force. Because gravity and spring force are used, in this example, the system consists of the mass, spring, and the Earth. The energy principle states that in an isolated system where change in energy is zero, such as the system under analysis in this lab, the change in kinetic energy plus the change in potential energy is also zero. This is critical to the analysis of the energy of the system over time. Kinetic and potential energy formulas were also used. To analyze the motion of the object, a large garment hanger, a spring, and two masses were needed. The spring was hung on the garment hanger. The two masses were hung on the spring, and the resulting lengths of the spring were measured and used to determine the spring constant K and the relaxed length of the spring L naught. These will be important for the computations. Next, the spring was held out to the side of the garment hanger and released. Its motion was recorded for a little over 9 seconds. The video of the motion was put into Tracker, and the position of the mass over time was recorded using Tracker's software, as you can see in this video.
And the X part is consistent throughout the thing. So that's like that one. Like I stared at for a good like 7 minutes.
The computation of the motion of the object was created by inputting several constants that were derived from the experiment and using them to calculate initial spring and gravitational force. Net force was found by summing the spring and gravitational force. Initial kinetic energy, spring potential energy, gravitational potential energy, and total energy were also calculated. Then, in the calculations loop, the velocity and position of the mass were updated using the velocity and position update formulas. These new values were used to update the gravitational force and spring force, which were then summed to compute net force. Kinetic energy, spring potential energy, gravitational potential energy, and total energy were also found with the new velocity and position data. This process was looped repeatedly with a short time interval between iterations to produce a result accurate to real life. The model was very accurate in predicting motion in the x direction. This shows that the model is correct in the prediction of motion for an ideal system. However, the model was rather inaccurate in predicting motion in the y direction. In particular, the mass started out moving downwards rather than upwards like the model predicted. This is likely because the spring force formula assumes that the weight of the spring used is negligible, but the spring used in the experiment was quite heavy. It was not measured, but its weight was similar to the weight of the mass itself. Thus, the spring itself weighed down on the mass, causing it to initially move downwards instead of upwards. The y position of the mass also did not vary as much as the model predicted, which may have also been because of the weight of the spring itself. Thus, it can be concluded that when predicting the motion of a mass attached to a spring, it is imperative to either account for the mass of the spring or use a spring whose mass is negligible. One potential error is that the mass made slight movements in the z direction as it moved back and forth, and the model cannot account for this slight movement. Despite these problems with the model, the energy principle held true for the model. The change in kinetic energy and change in potential energy canceled out at every time point to create a total change in energy of zero, which aligns with the energy principle's prediction for a system where no energy is inputted or outputted. One remaining question is, what are the oscillation periods of the motion of the object? Finding the oscillation period of the motion of the object involved finding when it reached the same point in the wave as it was when it started. These points are circled in the graph shown. The oscillation period in the x direction was around 1.402 seconds, while the oscillation period in the y direction was around 1.268 seconds. These values are very similar, however, they should be theoretically identical because the spring should theoretically oscillate in a perfectly even manner as seen in the model. This difference may be due to the errors already discussed or human error with recording the video. Thank you for listening to my lab report.